It's on? Yeah? Good. All right, so yesterday we talked about flavor in general, and then we did the counting of parameters for so physical parameters for the charged leptons, and I gave you homework to do the same thing for the quarks. And there I said that there's a CK matrix, which is where conventionally we put all the flavor violating parameters, and there are 4 of them, 3 mixing angles and 1 parameter and 1 phase. Today we'll see how we test this CKM structure. So that's really the goal of today's lecture is the CKM structure. Sometimes this is called also testing the KM, so the Kobayashi-Maskawa mechanism. I didn't comment on this. So the 3 generations are the smallest set of number of generations where you have this CP violating phase. If you had 2 generations, you only have a mixing angle, so no phase. There's no physical phase. That's one of the solutions or one of the ideas for how the CP could be realized, which was in the Kobayashi-Maskawa paper. So therefore, this goes under the name of Kobayashi-Maskawa mechanism. All right, so all flavor transitions are determined in terms of 4 parameters. And we'll use the so-called Wolfenstein parametrization, which I alluded to, but now I write it explicitly. So it takes this, the hierarchical structure of the CK matrix and introduces the parameters that are supposed to be order 1 or so. So minus lambda, a lambda cubed 1 minus rho minus I eta minus a lambda squared, a lambda squared. So there are 4 parameters here, a, lambda, and rho. So these are the real parameters. And then there's one imaginary part. So eta, if eta is non-zero, then we have CP violation. And this is good up to order lambda to the 4. And all this structure is fixed by demanding that the CKM is unitary. All right, so this is correct up to order lambda to the 4. All right. So instead of having 3 mixing angles, we have now 3 parameters. The first one is the expansion. And then we have 2 parameters, which are presumably order 1. And then eta is the imaginary part of the phase. Yes?
Just to be clear about this expansion parameter lambda, it's an observation that things seem to get smaller numerically, but there's no actual expansion that you've done in some underlying thing to get you that.
Correct. So the comment was that this, I'm talking about an expansion. Is this something that has some meat to it, or is just an observation and you just package these observations in terms of structure? So both can be true. So from bottom up, it's just you see what these numbers are, and you see that it fits nicely this pattern, right? So that's it. So you just use this parameter. I think that's what Lincoln Wolfenstein did. he realized that there's this, not all of the matrix elements were known, by the way, at the time, no? But if you impose the unitarity and you realize that this guy is very small, you could just postulate that this is the structure. You can get this structure, however, from the flavor models. So it could be that it is coming from some symmetry or quantum number assignments.
But not in the standard model.
No, in the standard model, it's just parameters. So that's why, this distinction between the A standard model. So a standard model could have a completely different CKM matrix. So all of them could be order 1. It's still, everything would be fine. The standard model that is realized in nature has this structure. And it controls the phenomenology, which, experimentally is very important if something is 10 to the minus 6 or if it's something which is 10 to the minus 2. All right. So all flavor transitions are controlled by these 4 parameters. So how do we test that the flavor violation is really coming from the CKM in the quark sector? Well, all the transitions are now determined by 4 numbers, and there are many things that you can measure. You open the PDG, there are many, many modes that are measured. Some are more useful than the others for measuring the CKM. So we'll highlight the ones that are useful. We'll focus on the so-called standard CKM unitarity triangle. All right, so what's done here is you realize that so the unitarity means that if I take, for instance, the first column and I multiply it with the third column complex conjugated, I will get 0. So if I take this column and multiply it with that column, I get something which is 0, complex conjugated. This is interesting because all the elements are now going to be of the same size. So 1 times something of lambda cubed. Lambda times something of lambda squared is also lambda cubed. And lambda cubed times 1 gives me 3 numbers that are of similar size. Let me write this in terms of the matrix elements. So remember V star is 0. So first column has VUD, VCD, VTD times complex conjugated VUB, VCB, VTB gives me 0. And all 3 are of similar size. They're complex numbers. So if you now were to just draw geometric picture, would be 3 vectors in the complex plane that add up to 0, meaning that they form a triangle. What's usually done is you divide by VCD, VCB star. So you normalize this. All right, so now this is blackboard. You can delete this and write 1. So this is the standard CKM triangle. So the plane is, so this would be rho eta. This is VUD, VUB star over VCD, VCB. So that's this length. This is 1, 0, because we normalized it. You put this in the origin. And all right, and then the angles here have names. All right. All right. So I don't know the whole history of how this naming came about. When I became a physicist, this was already set. But it's definitely true. The US uses or used to use alpha, beta, gamma. In Japan, it was phi 1, phi 2, phi 3. This was in the era of B factories. So maybe this is more historic than anything else. All right, so not all of the constraints will map onto this triangle. No? So if you're measuring something that has to do with the second column, of course, it's not going to appear here. But many of the constraints that we're interested in, why? The ones that will tell me whether or not I have CP violation do appear on this triangle. No? So that's why this is useful. So we'll go over the constraints. So let me try to know what this. So this is the complex plane. All right. So let's see. All right. So this is roughly where 1 is. This will be 1.5. This is eta rho. In the nodes, there are bars here up to order lambda squared correction. This is exactly rho eta. It's not so important, just that you're not confused. All right. So you see eta is order 1-ish. No? So eta is the imaginary value, and on this side it's rho. All right, so where to start? Okay. Let's see, I can squeeze a few things on the side. So the first one, let's do loop induced. There will be several constraints. So the first set will be loop induced. And will be meson mixing. So the final initial states are going to be mesons, and these are flavor changing neutral currents. So the ones that are forbidden at tree level, they're flavor changing neutral currents, they're forbidden at tree level. For instance, K bar mixing is a box diagram like this with a W. So it takes an S quark and converts it to UCT and then to a D. And you take an S bar and you convert it into a D bar. So on the left hand side we have what meson would be as SD bar. Ah, fantastic. All right. So it will take a K0 bar meson and converts it into a K0. All right. So on this standard CK unitarity triangle, this is a band like this. So this is K bar mixing. All right. There are more. You can do the same thing for B sub S bar. mixing. So it will take a B, converts it into an S quark, U, C, T, B bar. S bar. So this is the similar terminology. So BS0 bar goes to BS0. Now that is carves out a region, something like this. It's supposed to be a circle. All right, so that's all right. So you already see something quite non-trivial happening. No? I have a transition that is converting the second and first generation quarks. And in this case, you take the third generation quark, no? And they are pointing, I mean, at least they're touching, no? So now if you have more, let's say the next one will be bar mixing. Maybe I can cheat. So if I do, this will become a D bar, this will become a D, and then I have B0 here and a B0 bar there. Also gives a something like this. All right. All right, so that's now getting quite interesting because now I have three measurements and they still overlap in one region here where I suggestively drew the triangle. Then, so maybe this had something to do with the F's and C's. So if you add a completely different type, which is the charge currents, so charged current processes, all right. For instance, you can take B minus to D0 K minus type transition. So we'll talk a bit more about this later. So take a B minus, there's a S, K minus, and this is CU bar D0, all right? So it's a three-level transition. There's a matrix element here, which is BCB. And then I can do a similar three-level diagram. But instead of D0, this is D0 bar. B minus, U bar, K minus. If these two decay to the same final state, they interfere, and you can be sensitive to the VUB phase. So it's quite complicated. I'll come back to this. I'll say a bit more about what's going on there. But at the end, what happens is the constraint is something like this. That way. Yeah. right? So this was the B minus to the K minus. Again, it coincides. Can also take a different one. So let's say semi-leptonic decay nu. Set the bar. So I have a B0 bar, let's say that goes to pi plus. All right, so you measure the rate for this transition, and you are going to be sensitive to VUB matrix element as long as you're able to get that hadronic physics correctly. So that will be something like here. Okay. All right. It's getting busy already. So this was B to pi nu. And add one more. So you can also measure the phase of this mixing matrix element, and that's yet another constraint. Looks like this. All right. Okay, so this was also, well, should go a bit closer. This is also B. All right. That's it. There was many things. There's an extra one that I will not draw, but you already see, no? There's many lines. The most important thing is they all meet. There are many different measurements that you can do. The ones that are on the figure are the ones that are the most sensitive with controlled theoretical errors, so that you can interpret well what this implies for the CKM. So that's really a very striking test of the Kobayashi-Maskawa mechanism. No? So once again, it involved all three generations of quarks. No? There was B to C, so the third to second generation transition. There's the third to first. Only the first two, the loop level processes versus tree level processes, right? So it's really quite a striking test. Not surprisingly, there was a Nobel Prize awarded to Kobayashi and Maskawa. So the experimental facilities were where this is being tested right now. Or I should go back to the white chalk. So there is a Bell 2 in Japan. So this is an E plus, E minus that then creates B bar pairs. And then L8CB, which is at CERN. Okay, CERN. And then you have PP collisions. You also produce B quarks plus stuff. They hadronize, and then you can figure out what's going on. All right. Any questions? Two questions.
So what actually goes into all of these calculations? Like, they look very scary and hadronic.
Okay, so the question was, what goes into these calculations? They look very scary. That's a very good first impression. It is they are, so it depends, no, is the answer. So I'll do two examples where we are lucky enough that you can be ingenious enough, or you know lucky enough, whatever, that most of this hadronic physics cancels, right? The reason why that happens, I can comment a bit more. There are two different examples why this happens. The other thing that simplifies our life is that these loops, well, I shouldn't point there, that's the problematic one. But here, no? So these contributions are dominated by the top quark contribution. Since top quark is heavy, you can integrate this out. So to a very good approximation, this whole thing is just a 4 fermion operator like this. P S bar S B bar. So it has this structure. So it's just a 4 fermion operator. And this is something that luckily you can put on a lattice, so you can measure the hadronic matrix element of this thing on the lattice. Right? So the answer is lattice is a big input here. That's why I said the stuff that is on the board is the stuff that you have controlled theoretical errors. So partially this is due to because you can compute on non-perturbatively using lattice QCD. So this is one side. Here also, these matrix elements are such that you can compute on lattice because there's no strong phases here. I'll talk about this a bit more. This, no. But here there's an ingenious way of just measuring everything. It's quite striking. No? So you get rid of, you measure all the hadronic dragons, and you're able to extract the weak, the stuff that we're interested in. There was another question.
What about the parameter A? Is this plot for some particular value of A, or does it drop out?
So the question was, what about the value of parameter A? So in here, everything. So if you follow, no. So it's A times lambda cubed, A times lambda cubed, A times lambda cubed. So then you normalize, and A drops out. No?
Yeah. So you have to do different measurements.
Yeah. But that's a separate story. Yeah. It's not everything that is testing the CKM is on this plot. Far from it, no? Yeah. Anything else? Yeah. Yes.
I've heard that there is some anomaly that suggests CKM non-unitarity. Where does that come from?
So the question was about the CKM non-unitarity. So I'm probably you're alluding to probably Vincenzo mentioned this in the first week. It comes and goes. So right now I think it's in the first. So you can do different triangles. So you can ask also about the first row, adding. So you take the first row, square it, sum it up. It should sum up to 1. It almost does. It's like a maybe 2 to 3 sigma anomaly. There is nuclear physics involved because you need to measure the VUD very precisely. So this guy is 1 plus small corrections. There is also KM physics, which fixes this. And then there is a super small correction, which is irrelevant from the third guy. Yeah, it's there. It's been around for a while. I don't know what will happen. Yeah. Anything else? Yes.
Yeah, maybe it just follows up on Oliver's comment, but like I don't quite follow the motivation for this parameterization. Like it looks like in this unitarity triangle, you've already like ignored the order lambda for corrections. If I look at the left side of it, it looks like it would just not depend on rho and eta, but also on lambdas to the fourth, and it looks like you're not including that.
Yeah. So I think there were 2 questions hidden there. So the first question was, where does this the idea for this parameterization come from? So I don't know exactly what Lincoln was dreaming up and what inputs he had, no, but it is part of the clues line that Matthew had yesterday. No? So you take clues from experiment, right? And in this case, I don't know exactly how much it was known about the CKM structure where he wrote this down. But definitely right now, hindsight is 2020, you see that it's a good approximation for the numbers. There's one way of thinking about this is there's just nothing, just a useful thing to remember how big the CKM elements are. No? So if you want to have a mnemonic, it's a super useful tool because I can just count these lambdas. They have nothing to do with any structure. Maybe there's some structure underneath, maybe not, but it's just a mnemonic. No? So that's one view. I think the other question was about these lambda to the fourth corrections, right? So I mumbled a little bit that there's what's plotted really is rho bar eta bar, which is rho 1 minus lambda squared over 2, I think, is the rho bar. Okay, factor of 2, 2 is 3, is pi, is 10. All right. But there's a correction that you can absorb, and then it works to order lambda to the fourth. But you're right, you ignore the higher order corrections, but they are much smaller than this area here, so it doesn't matter. At the end, what you're really plotting, no, is not rho bar and eta bar, is this, no? And this has no approximation, so that's what you're really plotting, no? At the end of the day. Anything else? No. Okay. So, all right. So the plan for the rest is we'll do 2 examples in more detail, and then we'll also learn more about CP violation, etc. So the 2 examples that I picked is this one. So we'll look more into this complicated structure. And this, the BB bar mixing. All right? So we'll work more. All right. So the first one I want to do is the meson mixing. All right? So the mixing here means is that I take one flavor state and I can convert it to a different flavor state. This will lead to oscillations. The oscillations will be there because the flavor mass eigenstates are not mass eigenstates. So flavor eigenstates. So the flavor eigenstates are the B0, B0 bar. These are not mass eigenstates. So the mass eigenstates will be some linear combinations of the B0, B0 bar. Let's call them light and heavy. All right? It's good to pause a little bit. Now it's a peculiar thing that is happening. So I take one state, and now I'm able to convert it to a different state by doing this weak interaction. And again, I think Matthew had this totalitarity principle. So as in life, what is not forbidden is allowed. No, that's the totalitarity. So what is not, if not forbidden, then is allowed. All right. So for instance, could I have B plus, so that's B bar, mix with B minus? So can I write something like that for, I take a B plus, I do, I don't know, 15 loops in electroweak. At some point, I will be able to convert B plus to B minus. You're not happy, so why not?
Charge.
So the answer is charge, because there is a conserved U1 electromagnetic. No, I have a symmetry that forbids the mixing. So this is not allowed, right? However, there's nothing like it for flavor. I have flavor is violated, there's no symmetry, so I can write down already at one loop. You will be able to convert the mass eigenstates so convert the flavor eigenstates to a different flavor eigenstate. All right. I think I don't need this. Okay, so the mass matrix for B0 B0 bar system is mass matrix will look something like this. No? So I have the mass of the B0, then I can also take a B0 and convert it to, so I can take a B0 bar, convert it to a B0. So this M12 matrix element will be the hadronic matrix element of this one loop correction, or rather of this dimension 6 operator. And similarly for M21, M22. All right, so this is big, no? This is the B meson mass. What is the B meson mass? B meson mass. So 5 GeV. So there's an easy way to remember this. How many feet in a mile? Americans? All right, mass of the B. ME. All right, so for me it's the opposite. I remember how many feet in the mile because I know the B meson mass. It's a fine tuning, right? But you also need to take the look elsewhere effect into account. So there's a mass, one of the mass of many states matches something that is common to us from real life. So this is big, no? So this is basically up to corrections is this thing, no? This is the B meson mass. This is small, right? This is small. It is of the size, we can estimate this how small this thing is, right? It's gonna be, I said it's dimension 6 operator, right? So in the Lagrangian, it has to come with the suppression, which is W squared. It has a loop factor. There are CK elements sitting here. So there's VTB, VTD squared. In terms of the Wolfenstein parameters, this one is of order 1, and this one is. So third to first is very small. Lambda cubed. All right, so this is, so it matters, and then I need to have the right mass. So m b cubed. So you see very small. mb is much smaller than mw. 1 over 16 pi squared is 10 to the minus 2 or so. And this again is lambda to the 6. So it's a small number, much smaller than mb. All right. Now we know something about this, even without measuring. So CPT conserved means that the mass of the B0 and B0 bar need to be the same. If CP is conserved, then the off-diagonal elements are also the same. And as I said, they are much smaller than the diagonal ones. So therefore, this M, looks something like this. So it's big elements and then things super small on the off-diagonals.
Question?
Yes.
Do you know if those off-diagonal elements are bigger or smaller than the ones in the kaon sector?
So the question.
The kaon mass is sorry, the strange quark mass is smaller, but the CKM elements will be bigger in that case.
So the question is how it's about comparing the kaon sector to the B meson sector.
Whether the off-diagonal element is bigger or smaller.
So the so you lose. I don't know actually.
I was just taking this formula and substituting
the
strange quark
and you replace the MB with an MK, and you have VTD VTS sitting there, which is small.
Some things get bigger and some things get smaller.
No, VTD VTS.
Oh, VTS is bigger, right?
It's all So I think it's smaller, but what really matters is how. What is more important there? No, so for the kaons, it's very important that the decay widths are quite large, the differences. Well, here it's a small correction, in a way. But I think numerically they're smaller. Okay, so back to this. Now the mass matrix is big. These are exactly 1, and there's a small mixing parameter. But you know that if I just switch on a small off-diagonal, this will turn the mass eigenstates. That would be, let's see. So these flavor states are related by CP. If CP is conserved, right, then mass eigenstates are CP. Right? And they are, I think in these conventions I have the minus signs right. They are maximally mixed. Right? They're maximally mixed. So just turning on a small off-diagonal maximally mixes the B0 and B0 bar. Right? In this case. Now, in real life, there are two complications. So first complication is CP is violated. The first one is CP is violated. So M12 is not equal to M21. Okay, I mean, it's morally it's still a similar story. I have the light and heavy mass eigenstates are just now a linear combinations of B0 and B0 bar. So these are the two parameters that will give me the two mass eigenstates.
Are those rho and eta the same ones in the triangle?
Q and P. So Q, Q and P, yes. Yes, I'm so sorry. I don't know. I better not try. So Q and P. Any other comments? Yes.
So will some combination of these Q and P directly give you the CP violating?
Yes, so the question was, how will this be related to the CP violation measurements? I will talk about this next. So there's systematically we can go over this. Anything else? All right. And the second complication is B0 and B0 bar decay. All right, so I completely forgot about the decays. So before, this was closed system, it didn't decay. So this would be Hermitian matrix. Now, the B0 bar decay. So if I only look at the two-state system, I will be losing probability. You know? So if I start with a B0, it oscillates to B0 bar, oscillates back, but I have a leaking pipeline. You know, they're decaying away. So I have less and less of B0s if I keep measuring. So we have a non-unitary evolution. Okay, so it's described by non-Hermitian matrix. So the Hamiltonian used to be just this mass matrix. Now I have some I times gamma. Gamma is also a Hermitian matrix. This describes the decays. So these are both Hermitian. But the Hamiltonian is not Hermitian. Right? So if I now write the evolution, okay, so let me call B0 as a function of time is a B0 that starts as a B0, and a B0 bar is the state that starts as a B0 at t equals 0. Okay? So this will be now governed by this non-Hermitian, non-unitary evolution, right? And it's just parameterized by these two Hermitian matrices. So gamma. Right. So I'm not writing them out what they are, but in principle they are calculable. These guys just describe the decays of the B mesons, so in principle calculable. And now back to the CP violation. No? So now we're good. We have all the ingredients we need to understand what kind of CP violation we could observe. So first thing to note is CP violation is inherently quantum mechanical, right? Because you remember the CP violation was present only if we had phases that you cannot rotate away. No? We had to have a physical parameter that is just a pure phase. Well, only makes sense in quantum mechanics, no? If I have to talk about phases, I really need to have a quantum mechanical interference in order to extract this phase. Now, so if I want to do a measurement, yes?
So can't we still have a phase if we just have a classical complex field, like the pions or quarks fields?
Yeah. So the question is about classical complex fields. So I'm not entirely sure what you're getting at, but let me interpret this in two ways. So one is we have a complex notation in electrodynamics, classical electrodynamics. That's just a mathematical trick to solve differential equations more easily. So that's one option. I don't know if that's what you wanted. But there's also another option, which is that complex phases also appear just as scattering. And these are called strong phases, and I will comment about this. That's actually a very important point. So I don't know if that's where you were going with the pions. It sounded like that you were going for this. Does this make sense? If it doesn't, maybe wait a few minutes and then you can ask me again.
I'll ask again.
Yeah, okay. Anything else? All right. All right, so we're going after the phases. We need interference. So interference is the key. Right? If you don't have interference, it's always the interference, what interferes with what. And there are basically three categories of CP violating observables. So three types of CPV observables that you will encounter. The first one is called CP violation in decay. All right, so if I take a B0 decays to some final state and a B0 bar decays to some final state, let's call it F bar. Let me call the amplitude for this first transition AF. AF squared will give me the rate. Right? The rate for this decay is proportional to the amplitude squared. If this rate is different than for the B0 bar to F bar, right? So these are CP conjugate to each other. So I take one rate, and the CP conjugated process, if the rates are not the same, I have CP violation. So it's like the most naive, or like the gut feeling is that's the CP violation. No, that's how I measure CP violation. All right, so that's the first one. The second one, CP violation in mixing. All right, so now we go back to this Q and P. If Q over P is not 1, Q over P, if this is not 1, you remember this ratio was 1 for CP conserving case. This is called CP violation in mixing. And I'll say a little bit more about each of these cases. Let me list them first. All right. I think maybe I won't say much. Well, let me list them first. CP violation. The third one is, it's a mouthful, CP violation in interference between decays with and without mixing. All right, so let's construct an observable Q over P, AF over AF. So I take Q over P. This can be complex numbers. The amplitudes for the B0 and B0 bar decays. The decays now are in the same final state. These are all complex. If now the phase of this quantity is non-zero, then you have CP violation. All right, so the way, I mean, it looks weird, no? Where this comes from? Well, so let's say I start with a B0. The interference pattern would be you oscillate to B0 bar, and then this thing decays to a final state F with a probability AF bar, or you directly decay to a final state F. So the oscillation part knows about the Q over P, right? And then the two other parts know about AF and AF bar. So at the end, if you have an interference pattern here, this is the observable that has an imaginary part which is non-zero. Yes, the question.
Aren't F and F bar different final states?
Yeah. So this, I pick a state which is the same as F bar. Let's say K short. I don't know. It's psi. So this is a CP eigenstate. This is CP eigenstate. So both of them are also CP eigenstates. Yeah. Before it didn't matter here. All right. Okay. So, I hope you kind of can see that something like this could have to do with CP violation, no? It's the interference pattern, and I'm picking up an imaginary part only, no? So, yes, there was a question.
Should we interpret A bar F as the amplitude of the conjugate process and not the conjugate of the amplitude?
Yes, absolutely. It's the amplitude of B0 goes to F.
And A conjugate, like...
Let me be more precise. Very good. Okay. So let me talk about CP violation in the decay. I think that it will be maybe much clearer.
You got about 15 minutes, by the way.
That's perfect, I think. Yes, I'm good. Yeah. All right, CP violation in the decay. So I said, let's define this is the amplitude of B goes to F, call it AF. A bar, F, I called amplitude of B bar goes to F bar. The asymmetry so different font. All right. So I take the rate for B bar goes to F bar minus the rate for B goes to F. plus the same thing. So I normalize it. So this would be 1 minus a over a bar squared, 1 plus a bar squared. Okay. So now let me assume that there are two interfering amplitudes. Let's just take this case. So let's say that I have two interfering amplitudes. Small a1, that's the amplitude, has a phase, and I will write two phases here. And it will become apparent immediately why I write two phases. All right. So the first phase is the phase that is appearing in the Lagrangian, so one of the CKM elements times the CKM phase. The second one is the strong phase. The strong phase will have to do with the rescattering. All right, so this is Wick's case, weak, strong phase. All right. This is the phase that flips the sign when I go to the conjugate decay. So the weak phase flips the sign. The strong phase doesn't because it has to do with the rescattering. I will come to this and say a bit more. So delta 1 plus a2 e to the minus phi 2 plus I delta 2. So pictorially, I have two ways of going from B to F. You can take the A1 route, e to the I phi 1 plus I delta 1, or the A2 route. If I take B bar to F bar, the weak phase flips the sign, but the strong phase doesn't. In the limit of one of the two being small, just so that it's easier to talk about, then the CP symmetry goes as A2 over A1. Has to go as the smaller of the two, because if I completely set A to 0, then the absolute values of, there's a bar missing. The absolute values are the same, no, for the two matrix elements. All right, so it has to go as the smaller of the two. However, it also goes as the difference of the weak phases and the difference of the strong phases. So in order to see the interference pattern, it's not enough to just have the weak phases. You also need to have the so-called strong phase. Right? So what is this thing? Here, I can't believe this. The strong phase is, for instance, let's say we take, let's say I imagine that I take a pion, pi plus, and pi 0, and I scatter them. So I have an incoming pi plus, and pi 0. I scatter back to pi plus, pi 0. If the invariant mass is close to the rho meson, mass will create a rho meson. So in principle, you could create a rho meson here. All right, so the amplitude will go as the Bright-Wigner, where this is the rho meson mass. Right? So this has, you see, has a phase, is non-zero, and is a function of S. Right? So if I look at the cross section, to look something like this. we have a rest at the mass of the rho, but also the argument of this amplitude, which I call the strong phase, is non-zero. No? It goes from 0 to pi. Plus pi. All right? So this thing has a phase. It comes from the rescattering. If I take the pi minus, pi 0, so a conjugate state, CP conjugate state, well, it's going to be exactly the same. No, it creates a rho meson with the same mass. It's just rho minus instead of rho plus. So I'll have exactly the same Bright-Wigner, right? So you see there are two sorts of phases floating around. One are CP conserving, and the ones that are sitting in the UV Lagrangian, the standard model, they're CP violating. There's another example that you can think of. For instance, questions?
I was
Yes.
just going to ask what the x-axis of that second plot is. Is that also S?
Yes. S, and it's totally hidden from your view, so yeah, S, good. All right. Like there are more phases you can think of in quantum mechanics. No? For instance, just propagating waves. No? So imagine that you have a two-slit experiment. You shoot electrons here. No? Have an interference pattern here. If I shoot E pluses, doesn't matter, it will be exactly the same interference pattern. No? So this path is another, like e to the I, the path is another CP conserving strong phase. That has nothing to do with this rescattering. All right. So I have 10 minutes to now come back to the CKM elements. It's too bad I deleted. All right, so the first one was, I said this, maybe I'll just write the two diagram again. So now we understand, maybe roughly. So I had a B minus, which was U bar B C, the W, U bar S bar, D0, K minus, and then there was another diagram. No. B minus B to U, D0 bar, C bar, S bar, with a U bar, K minus. All right. So the first thing that needed to happen was this D0 and D0 bar, they need to decay to the same final state. Right. Now I have a way of having two amplitudes that can interfere. They come with different CKM elements, like this one is VUB. This is the one VUB had the phase, and this phase is, I don't know how we call it, delta CKM or gamma, different names, but it's the phase of the CKM phase, no? The one that I had in the very first lecture. So by interfering these two, you will be able to pick up the phase. However, it's not enough, no? You also need to have the strong phase coming, and it's to also be able to control the hadronic physics, right? And that's where the magic comes in, is that D0 and D0 bar are weak decays. So they propagate and then they decay. So the branching ratios are basically this amplitude times the amplitude for the d decay. Right? It's like the narrow width approximation, if you remember, but at the amplitude level. So that's number one, no, is that I can have these products of, I have first the product of the B decay amplitude times the product of the D decay amplitude, plus on the same from here. And then the second ingredient is you can have many different F's sitting here that will come from different, with different strong phases. The end result is that there will be hadronic matrix elements that you can measure because now I can pick the number of observables is quadratic in terms of the unknowns. Or quadratic because I have AB times AD. Does this make roughly sense? So that's the trick, no, is you can measure everything because you have many, many measurements that you can do that are correlated. So you don't have to calculate anything. It's really fantastic. No, you don't have to calculate. It's the best thing ever. You just hand this thing over to the experimentalists. So that's how this measurement works, and that was this gamma measurement here. This is in principle the most precise thing we can ever measure because the corrections are the order of 10 to the minus 7, theoretically. So as long as you build experiments, you will know how to measure this, all right? It's not true for all the others. The theory is much harder. So I have 3 minutes to do the B-meson mixing. And there, the important ingredient was that so the really important ingredient was, so you do B0, B0 bar mixing. And what is measured, let's talk about this part. So this thing is called sine to beta. Beta was this angle in the CK unitarity triangle. Sine to beta is the imaginary part of lambda f, where you are smart and you pick f to be k short j psi. Why you want to do that is because it's dominated by just one transition. So you do this is C. So it's a 3-level guy. It's just one amplitude that has no CP phase in it. Lambda f was Q over P, AF bar over F. So when you look at the CP conjugated mode, this part is just 1 times the CKMs. All right, so all the hadronic physics is just 1, cancels out. And here, Q over P, again in this, I think I deleted. So this came from the loop that was dominated by the top, B to D. So Q over P is again just some CKMs, all right? The hadronic matrix element again cancels because it's dominated by one loop. So that's why this is quite precise. The corrections are, of course, these things have corrections. It's only to leading order, but they're at the percent level, right? Okay, so I think I have to stop now. No, it's 10:15. All right, so if there are questions, so there's a little bit more details in the notes, but we got the gist of what's going on. Then on Thursday, I'll talk a little bit more about how you search for new physics using these measurements, and then we'll switch to the charged leptons. So that's the plan. All right.
only quantum mechanical if the classical fields are also complex for the fermions.